Hey, welcome back to the channel here. Today I'm looking at morphine. What is morphine? Well, morphine is probably one of the more common painkillers available, and it's very effective. It's also known as morphium, and it's an opioid analgesic. That means it comes from opium, the opium poppy, for example. That's Papaver somniferum. And so it was actually discovered back in, morphine was first isolated in 1804 by the German pharmacist Friedrich Serturner. And so he first isolated it as a medicinal alkaloid from the plant, and then the company Merck commercialized it in 1827, and then it was very widely used when the hypodermic syringe came out in the 1850s. Then we found a really effective way of injecting morphine in, and it was very effective at treating pain, especially in battlefield type injuries during the wars, during the Civil War, during that sort of thing. And so it's been very effective. Now, what it does is morphine has an effect on the nociception response. Right now, what is nociception? That's the body's way of telling the brain, hey, we've got some sort of danger. We've got essentially pain going on, right? So that can either be like a chemical pain, such as if you've ever taken capsaicin from chili peppers, you get that burning sensation because that's the capsaicin interacting in the body, and that gives you that sensation. Of course, we can also have actual thermal pain, which would be extreme hot and extreme cold. So that would be actual temperature, not just the capsaicin. But also you can have crushing pain, right? So if, for example, if you've been shot by a bullet, or if you've got if your hand is crushed underneath a car, for example, that's crushing pain. Opiates are very effective at treating this pain, right? Now, that pain relief, that analgesia that you're getting, is not without danger, right? Because the main issue with opioid analgesics is the addiction, right? They cause dependence, and so that's why you don't want to take opioid analgesics for a long period of time, because then you'll get addicted to them, and then you've got other problems, right? And there are some other side effects. Most of these are kind of minor, like drowsiness, euphoria, nausea, dizziness, sweating, and constipation. Those are possible side effects. The three major side effects, however, and these are the potential ones that might be more serious, would be a decreased respiratory effort, so that would cause difficulty breathing, vomiting, and low blood pressure, right? So obviously, if you've got low blood pressure, that can cause serious issues. That could cause you to pass out, for example, or obviously vomiting, that can cause major issues with your water and electrolyte balance, so that's also an issue. So the search for other opioid analgesics is obviously a big thing, or even less dependent opioid analgesics to deal with the addiction issue, right? So let's look at the structure of morphine, and let's figure out why this is so effective and why it gets into the body. So if I go here to PubChem and I do a search for morphine, here's morphine, and this tells me my compound. Obviously, it's a pretty easy drug to find. Here's our structures. We have some primary hazards. Our molecular formula just tells us we have some carbons, hydrogens, nitrogens, and oxygens present. We have a couple other synonyms here. We can expand that. These are all possible names of morphine. everything all the way through to the IUPAC names as well, which are unpronounceable. And then we have other information here. We can go to, whoops, yeah. So this also tells us a little bit about the drug under the description. It also tells us this is a DEA Schedule II controlled substance in the United States. Schedule 1, of course, has no accepted medical benefit and a high potential for abuse, so those are illegal no matter what. Well, morphine is not completely illegal. You do need a prescription. It is Schedule 2 because of its high potential for abuse, right? And but it's also very effective as a painkiller, so I don't think hospitals want to completely get rid of it, right? So major caution right there. And if you want to know more, you can click on more information about the legality of the drug. Then, you know, there is also a couple of links like codeine, fentanyl. These are other drugs. Methadone helps to treat some of the dependence issues. Hydrocodone and oxycodone, of course. Hydromorphone, meperidine. These are all other compounds as well. So let's download the structure. Now, if we look at the two-dimensional structure here, we kind of see at the top we have a phenol ring, that phenyl ring here. Then we have a 5-membered oxygen-bearing ring, and then we have another non-aromatic ring here with an alkene. So this is like cycloalkene. And then there's this ring up here. This is actually 2 fused rings because this nitrogen, there's 2 carbons that come up, and so this kind of forms 2 fused rings. It's a little bit easier to see in the 3D structure. So there's really 5 rings in morphine right there. Let's actually come down to get the SMILES code, and I like to copy the SMILES code right here, Control-C, and we're going to open up my visual molecular viewer, MO, and we're going to visualize the 3D structure. I'm going to copy and paste into the SMILES code here. We'll do morphine, and here's morphine. I'm going to add a ball and stick representation, and let's kind of look at it kind of this way right here. And I'm going to add my force field, and let's just give it a little bit of optimization just to let it relax. Morphine, you know, we say optimization to let the molecule relax, and yes, morphine will definitely relax you, right? Because of that nociception, that analgesia. So, but we've just relaxed energetically. We did 251 energy evaluations to relax our morphine to a 6.91 times 10 to the first power kcal per mole. Right? So morphine is now relaxed. Don't you feel better? All right, now let's see what we've got here. So here's our rings. Here's our first, second, here 3, and then this is that. So if you look at this up here, right, we have kind of a bridge, right? And so the nitrogen's in the bridge, and so there's 1 ring on this side and then 1 ring on this side. So that kind of gives morphine a little bit of a an A frame or an A shape, or you know, it kind of gives it kind of a triangular shape, which is very important for its interaction in the body, right? And so the next thing we can look at are some of the pharmacological properties for why this gets into the body so effectively, right? So let's go under ligand properties, and of course now we want to look at the bioavailability, and so that's called Lipinski's rules of 5. And so these are a set of rules that are based on multiples of 5 or 10, right? And so we want to get into the body to maximize how to get available into the system. We want small molecules, a molecular weight less than 500 grams per mole, right? Now, morphine meets that, 285.34. So we've got, we meet the first of Lipinski's rules of 5. Secondly, we want a log P of less than 5. Morphine is 0.88, right? And so the log P is the octanol water partition coefficient, so it's octanol over water. And so the higher your log P, the more hydrophobic it is. And that means it's more likely to cross membranes in the cell and get into the cell. We do have a fairly low log P, and that's mainly attributable to some of these polar these polar functional groups, such as the phenol and the alcohol and the ether, as well as the nitrogen. We still have a log P of less than 5, so it won't be too hydrophobic, so that's good. So we meet Lipinski's log P criteria, right? The other thing we want to look at is the number of hydrogen bond donors. That's this don 2. So we have 2 hydrogen bond donors. That's the OH, the phenol, and the alcohol, right? Because we have a hydrogen on our oxygen, and we have 2 of those, and then we'll form hydrogen bonds with other hydrogen bond acceptors. And we want less than 10 hydrogen bond acceptors. That's things that will accept a hydrogen bond. So generally polar atoms like an ether oxygen, the phenol, because that's the other end, right? The oxygen end, the alcohol, the other end of the alcohol, and also the nitrogen. That makes 4 hydrogen bond acceptors. Now, many people don't realize as well, but this phenyl ring itself, right? The phenyl ring is electron rich because this is all in resonance, and there's pi electrons all throughout here, and it's a nice little circle. The phenyl ring on here is itself a hydrogen bond acceptor. And Max Perutz back in the 1980s actually published on this, and it's pretty widely accepted that the phenyl ring will also serve as a hydrogen bond acceptor as well. So really we have 5 hydrogen bond acceptors in morphine. We're just not picking up this phenyl ring, right? So that's one thing that you kind of have to use your own intuition on, right? So that's the structure of morphine. Now the other thing to look at is TPSA. Now what's that? That's topological polar surface area. And so what is that? That tells that that's the surface area of all of the polar functional groups, right? Not the total surface area, just the surface area of the polar functional groups. And we don't want this to be too high because, again, we need this to be able to cross a membrane, and so we need more lipophilicity. So generally the topological polar surface area we want to be about 90 or less, take or give. Again, these are kind of estimate numbers. Don't get hung up on the actual number, but these are kind of guidelines. Topological polar surface area is not necessarily part of Lipinski's rules of 5, but it's also included as well. Now, if we look at the surface area, we can actually visualize that by going to surfaces and maps and molecular surface. And spell this morphine. Oops. There we go. And we need to select all the atoms here. Okay, molecular surface, morphine, and I want selected atoms and selected atoms, right? Now, if I visualize the electrostatics on here, right, where negative is red, positive is blue, I can kind of visualize the different parts. Now, I can kind of make this somewhat translucent there, right? And so this is basically, if we look at the molecule, right, the structure of morphine, that, you know, when you look at the atomic structure, that's where the atoms are, but those atoms have space, right? And so when we look at this, this type of molecular surface, this is what the molecule would actually look like if I was looking under a microscope. Minus the colors, because those are arbitrary, because, you know, everything in red is kind of, you know, that's where our polarity is, right? That's negatively charged. Things like, you know, the hydrogen bond donors will have a blue, so that might be partial positive there. We do see a lot of white, which is just neither positive nor negative, right? So this kind of helps us visualize that polar surface area right there, right? So we can kind of look in here. So that's one way of looking at morphine, right? Now another thing to consider, so this is where it gets really exciting. Let's see if we can make a better morphine, right? So, and you know, some scientists actually recently did this, right? So there's actually a paper that was just published. This was just published this year by Akiyama and co-workers. This group right here is out of the University of California at Berkeley, and they studied the synthesis and biological activity of carbamorphine. Now, what's carbamorphine? What they did was they took an oxygen to a carbon or a methylene replacement. The CH2 is called a methylene. And so they replaced that in the E ring of morphine. And what they found was this actually helped to relieve some of those critical side effects. So it actually made the morphine a little bit, it helped mainly with the lowered respiratory activities. So it helped alleviate a critical side effect where patients would have difficulty breathing, right? And so that's actually critical. And they also found it was still very effective at its nociception response and its analgesia, right? So that was actually critical. They actually synthesized it. Here's the complete synthesis. If you look at number 15 and 16 in the synthesis, this actually kind of shows a modified Diels-Alder reaction in here. So that was kind of interesting. And so they actually came through with the complete synthesis. Now, why are we synthesizing it? You know, most of the time morphine, we're isolating it from poppy. We're going to let nature do its work, right? So we're going to do biosynthesis. But sometimes if we're looking at modifications like this, like we want to remove the oxygen, there probably isn't a biosynthetic pathway to do that. So we need to have a way to synthesize it ourselves. So hence, here is how we can do that ourselves. Now in modeling, we can just simply take that oxygen, we can make it a carbon, we can just modify that ring, and then we can see what it's going to do to the structure. Now whenever I modify, we need to make sure and fix my charges again. Energy minimize, and here's my modified morphine. So you'll see this ring over here, this used to be an oxygen, that's no longer an oxygen now, right? And it kind of modified the structure just a little bit. We now have one fewer hydrogen bond acceptor. We do have a little bit higher log P. We also modified our topological polar surface area a little bit, and we didn't really make too many changes to our molecular weight. So we're still within Lipinski's rules of 5. And so this molecule, this is a modified molecule that is really effective. Now it's early. This paper was published in May, so there's a lot of research to be done, but this may be a potential new opioid analgesic which could help alleviate some of the adverse side effects of morphine. So, and so there is that's how medicinal chemistry is done, folks. That's what it is. So I hope you enjoyed this video here. And if you have any questions, go ahead and leave them in the comments below. Don't forget to kind of like and subscribe the video. I think that really helps. If you want to learn more chemistry, you want to keep updating, keep ahead and subscribe to my channel, and I keep publishing some very interesting stuff. So for now, I will bid you farewell, and we'll talk more again. Thank you for watching.